All right, everybody. I'm excited now. We're entering the last phase of the conference. All right, we are at the end of the day. It's been a fun day, but we're almost done, which is great. Not gonna lie. All right, but we have some awesome talks coming up as well. We are moving into our open track part of the competition, and to kick things off will be the open track data software winner, and that is Brandon Onyejekwe. All right, there we go. Didn't do so bad there. Quantifying uncertainty in marathon finish time predictions. Brandon's a recent graduate from Northeastern, Bachelor of Science in Data Science, minor in Mathematics, sports fan, the captain of Northeastern's club running team, member of their sports analytics club, and he's also currently doing half marathon training. And I just speaking with him earlier, is interested in PhD programs too. So let's give a big round of applause to our open track data software winner, Brandon.
All right, thanks. Hello, everyone. Thanks for having me. I'm here to talk about marathon finish time predictions. Brief overview. A marathon is a long distance road race. It is 26.2 miles. It's made up of a large collection of runners, usually hundreds or thousands of them, and they all compete on the same course. Here are pretty pictures from the Boston Marathon because there are no videos that'll make it look as exciting as copy, unfortunately. In addition to the runners, there's also a large collection of spectators making up friends, family members, coaches, general running enthusiasts that are spread out along the course, typically located at a single location on the course because it's hard to navigate and move along to different locations. And so as a spectator located at one part of the course, looking out for your specific family member who's running, it's very hard for you to figure out like when your family member is going to finish, how they're doing in the middle of the race, when they're going to pass by you. And so these are interesting problems in which there's very limited information for you to go off of. One piece of information that helps provided at many major marathons is splits. Splits are kind of like checkpoints where after a runner crosses a given interval, the marathon reports the time that they crossed at that interval. And then that's usually posted on like a website or like an app. So you can see, for example, when your runner crosses at the 10K mark, what time they crossed. And then you can use that information to make better predictions or have a better assessment of when people are going to finish. Further, most major marathons have their own predictions that allow you to look at a well-defined estimate for the finish time. And the methodology that they use is the following. So if you look at, for example, the 10K, if the runner crosses 10K at 40 minutes, you extrapolate that time for the whole distance, and then you assume that that pace is going to be held constant for the rest of the race, and then that allows you to arrive at a prediction using that calculation. And then at 20K, you discard the previous calculation and you do the same thing again, use the 20K split, you take that time, you extrapolate it for the 42 kilometers, and that's your new prediction, and so on. There are problems with this prediction. The two main problems are, one, the main one, which is that the estimates don't consider any in-race context that allows you to determine if a runner is likely to finish faster or slower than the observed pace. The most obvious statement about that is that runners empirically usually finish races slower than they start due to fatigue, lack of race preparation, and so on. And the traditional methods don't take this into account at all. So it would be nice if we had a prediction method that adapts to what we empirically see in data from marathon runners. In addition, the predictions are just a single point estimate, which is fine, except it doesn't give you any assessment on the uncertainty behind the estimate. So if I were to tell you, I think you're going to finish a marathon in 3 hours, are you supposed to intuitively think 3 hours plus or minus 5 minutes, or plus or minus 20 minutes, or plus or minus an hour? There's not really a good assessment as to what the numbers mean. And we would like to have a prediction that gives us a better assessment of when we think people are going to finish. And then just to motivate the first problem a little bit more, so if you focus on just like the green dots, for example, those are for every runner. If you take each runner's 30K split, and then you use that to make the traditional prediction by just extrapolating it, that's the x-axis, their extrapolated predicted time, and then the y-axis is their actual finish time, and you can plot that distribution for each runner. The same thing applies for the orange dots with their 20K splits and the blue dots with their 10K splits. And then you can see that all the dots fall on like this line that's not exactly correlated with the red line. The red line being that like identity function where they match up perfectly. And ideally, if the traditional method was a good estimator, all the points would lie more or less on the line, or at the very least would be just as likely to be above or below. But most of them are above the line, which again matches up with the fact that runners are typically slower at the end of races rather than the beginning. So I've identified problems. How do we fix them? There are two approaches that allow us to address both of the issues that we presented, allowing us to have a better estimate, but also one that places bounds on our uncertainty behind the estimate. Bayesian linear regression, in short, is a method that uses Bayesian statistics to place priors on the parameter of the linear regression model. And then in doing so, you can get a distribution, a posterior distribution of possible finish times. And since it's a probability distribution, not only can you interpret the median as like the point estimate, you can also use that probability distribution to place credible interval bounds to say how certain you are a runner is going to finish within this interval of time. And then similarly, but distinctly, quantile regression is another method where instead of traditional linear regression, which estimates the mean of the response variable, quantile regression estimates the quantiles or the percentiles. So not only can you estimate like the median, which we can use as our point estimate, but we can also estimate, for example, the 75th and 25th percentiles and use that as a bounds for a 50% credible interval. And we can interpret that as a measure for uncertainty quantification as well. And so we implemented both of these in Python using the PyMC and stats models packages, respectively. For our data set, we used Boston Marathon data. We scraped data from the Boston Marathon website. Limitations on why only using Boston Marathon data is not the best will be discussed later. But the main motivation was to examine the Boston Marathon. We have data for 14 years worth of runners, and we have each of their splits. We split training and test sets accordingly. And then as for the methods to how to specifically specify the linear relationships, there are three options. Method A is just the traditional method, assuming that the current pace is going to be the same as the finished pace, which is used by traditional methods. Method B is saying that the overall pace so far is a predictor, but is not necessarily equal to the final pace. And then method C includes that and another variable that we included that we call the current pace, which is basically taking the split from the most recently completed 5K as like a proxy for how fast the runner has been recently going. And so we apply methods B and C to each of Bayesian and quantile regression, and we have 4 models to compare to the extrapolation traditional method. And so results, we see that like interpreting this graph, the x-axis is at each stage of the race independently. We look at the prediction error, the root mean squared error in minutes across all runners. And we can see that overall, the models have very similar prediction errors and are all significantly better than the traditional model in blue. Specifically at the beginning stages of the race, if you look at 5K, 10K, and 15K. That's a very wide gap between the 4 colored models and the blue model. And that's important because at the beginning stages of the race, that's where you find the most uncertainty. And so you want to have better predictions there. And so that's good that we have a model that allow us to have better predictions at those stages. Other things to note, the method C models in green and purple with that extra predictor with the current pace seem to perform slightly better than the method B models that only have the single predictor. And then also something to note, because it's kind of sticks out, is that there's this increase in error for the 40K for the method C models, which we don't have an explanation for at this time. That's something we're still looking into. But again, what we wanted to focus on was at the points with the most uncertainty at the beginning of stages of the race, we're able to have predictions that have that are better. And then as for validation steps, we had 2 checks to make sure that these models fit our intuitions. So everything I talked about was just for the point estimates, but we wanted to place validation on the credible intervals. So the first thing we did was check that the credible interval sizes fit our intuition that they should decrease over time, because you should be more certain about the race in the later stages rather than the earlier ones. And we see overall they trend downward. Again, there's some issues with 40K, but overall they trend downward, they decrease over time, you become more certain of your estimates. And then secondly, we have another validation step, which is that if we have a credible interval, say of like 50%, we would expect about 50% of the runners to have that interval fall within their finish time, which is not, it shouldn't be exactly, but that's kind of like a rough basis of what we wanted to follow with our intuition. And we see that generally for 50, 80, and 95%, they're generally falling around the ranges that they should be, which is a good check that the models are at least close to what we want them to be. And so we developed an application for this. Here's a QR code for it if you are curious. So basically this allows you to simulate races in real time. So there's an option to enter a time. It'll give you this distribution. It plots a distribution of the posterior finish times for the Bayes 1 model. And then it also gives you the table that gives you the median and the credible interval sizes at different credible interval sizes. And then you can iteratively update that with your 10K time, 15K, 20K time, 20K time, and it'll update the chart accordingly. So for conclusions, limitations, and future work, in general, the models outperform the traditional method, which is good. We want predictions to be better. So it's good that we have a method to do so. Things that we want to do better, we want to choose better predictors, for example, or at least include better predictors that allow us to make better predictions like age and gender that we do have access to. And even things that we don't have access to would be very influential to help us make better predictions. Like, for example, the experience level of a runner has a big impact on how well they will pace. We only implemented the Bayes 1 app. The Bayes 1 model in the app, it would be cool if we implemented more. Only implementing the Boston Marathon for this means that it doesn't really apply to other marathons. You would have to change the data because courses have different distributions of runners and different courses that'll have people pace differently. So implementing more races would be something we'd want to do in the future. And then finally, it would be cool if not only to estimate when runners finish, but also if we can estimate when they reach a certain checkpoint along the race. For example, if you're stationed as a spectator at 30K, trying to estimate when they will reach the 30K mark rather than the finish time is another future goal. And that is all I have.
Yeah, we're gonna move over. You'll be able to ask Brandon questions, in the upcoming networking session taking place after we wrap up here. But big congratulations again to Brandon for our winner of the Data Software Open Track competition. And you can check out his paper online on the conference.